from the previous results, jk is 1 plus j square root omega mu sigma over 2. And that was under the assumption that the conductivity was very large, so in a good conductor. But jk, and then remember that that appears in things like this, e to the minus jkz. That's a wave traveling to the right. And normally what we do is substitute that in. And so we can write that as jk is e to the minus alpha plus j beta z. And we've seen that before in transmission lines. Notice that in this case, 1 times this and j times this, so alpha is equal to beta. And that, of course, we can see directly is just this thing here. Now, what we're interested in is if we look at the electric field, let's just call it E for simplicity, a component, so it's EXS. And it's going to have some amplitude that we could call EX0 times this thing, e to the minus alpha plus j beta times z. Now we can expand out the exponent, so we have an amplitude term that's decaying and minus j beta z.
This looks familiar.
Looks familiar from transmission lines, right? So alpha before had units of nepers or nepers per meter, and here's the value of alpha. It's right here. So what we'd like to look at is the scale of the amplitude. So when z increases, as the wave is traveling, it diminishes, and the diminishing factor is frequency dependent. So what I want to do is ask the question is, at what value of z does this thing become 1? So this is like sort of like a time constant, but it's going to give us the depth, not the time at which this becomes e to the minus 1. And the power, of course, will go to e to the minus 1 squared, e to the minus 2, which is roughly something like a tenth in very rough terms. So if we look at that, this gives us a scale factor. So when is that equal to 1? That'll give us a scale. So alpha z equals 1 means that this thing here gives us that z is equal to 1 over alpha, which is equal to, well, just take the reciprocal of this, 2 over omega mu sigma. So that is the distance at which the amplitude becomes e to the minus 1. Now that distance has a special name. It's called delta, and delta is the skin depth. And we can see that it's frequency dependent, and so we can actually look up the value of this for different materials. So let's say copper. Delta of copper is equal to 0.066 over the square root of the frequency after you do all the algebra with the sigma and the mu. And that's going to be in meters. And when omega is 60 hertz, when f is 60 hertz, delta is about 9 millimeters, which is really small. That's at 60 hertz. Now, normally when we have copper and cables, we're dealing at gigahertz. So this thing is going to shrink to almost nothing, very small. 5 orders of magnitude or 4 orders of magnitude smaller than that. So divide by 10,000. That means that the current is going down the cable is going to be limited to a very kind of narrow cylindrical annulus. So it's going to be a cylindrical ring. That means that the resistance of the cable goes up as the frequency goes up. Right.
Through the roof.
Through the roof. So that's the important piece about skin depth. Now, what effect does it have on the power? And in order to do that, we have a bunch of algebra to do. I'm not going to do it all. I'm just going to give you the idea of what to do. Is we need to write the magnetic field in the y direction corresponding to Ex in phasor form, then multiply by the time variation, take the real parts, or just stick with phasor form, and we know that to get the time average power, and that's going to be going in the z direction, it's 1/2 real Ex s multiplied by Hys conjugated. So the only thing left to do is to do this. I'm not going to do that here at the front, but I'd like Sam to tell us how to calculate Hys.
I'll do that.
Okay.
Let's use a green instead.
Let's use a green one. Sam gets to use green, and I use blue.
Well, I guess first we got to find out what H is, right?
Yeah, that's all I want you to do. We're not,
okay.
So what's Hys? Maybe you want to put a little line there so we... Yeah.
Hys, well, without the complex conjugate first. If we think back on the transmission lines, the way to get currents is to do V over Z. So we've learned about the eta business. So here we just do Ex0 over eta,
yeah,
right?
Times all this stuff.
Times that.
Yeah, put that
in. Eating up the J again.
Yeah. So now, can you remind us what eta is? Eta is the square root of... do it down here.
Eta would be square root of
mu
over epsilon.
Effective.
Effective.
Now, epsilon effective, remember what this is? Square root of mu epsilon effective is epsilon minus j sigma over omega. But we know that this is much bigger than this.
Mm-hmm.
And so we have that.
So that explodes and epsilon is caught in the explosion.
Yep. So sigma is bigger. So we've seen this before. Now the only thing we have to do is, well, we know how to do this. We've done it before. And we have to be careful. What do we have to be careful about when we compute expressions like this?
Well, there's that complex conjugate, so don't we need to be careful of sign?
Right. We have to be careful when we take the Hys conjugate. Eta's downstairs in the denominator, and we're going to have to star it before we take the real part. So you have to be careful. So we have the star effect here, but also the eta, which is something new. And then you can straightforwardly calculate this out and express it in terms of sigma and the skin depth. And the job is yours now to work all this out.
Well, I think it'll be a fun class.
Yeah, great. Practice with complex numbers.
Complex numbers.